Okay, in this video I'd like to walk through the basics of lenses. In our last video we looked at refraction and Snell's law, and we learned that when light passes through some new medium, maybe water, maybe glass, maybe diamonds, plastic, then that light bends. And we make use of this bending of light, especially with convex and concave lenses. So, imagine I have a convex lens here, and I have some ray of light that comes in and strikes the surface of the lens. Knowing what I know about Snell's law, I could draw a normal line where the ray hits the lens, and I could measure the angle in, and knowing the indices of refraction of these two materials, air and glass maybe, I could figure out the angle that the ray emerges on the other side. Since it's going from fast to slow, I know that this ray is going to bend towards the normal. So maybe something like that. But now it has another interface. Now, the angle coming in with respect to a new normal, I'm going to go from slow to fast, and so this light ray will emerge making a right-hand turn. So two right-hand turns are going to happen with this ray. But another ray on this side, I could work out with Snell's law, the angle in, the angle out, bends towards the normal, then bends away from the normal, and I'd find that these light rays coming in parallel would converge. And in fact, all of these parallel rays of light would converge. In a convex lens, this is a double convex lens. It's curved outward on both sides. You could have a planar convex lens. There's different shapes. But when it's thicker in the middle and thinner on the outside, we get light converging on a focal point. And we could call this type of device a convergent optical device. Now, if you think back to what we learned about mirrors, with mirrors, concave mirrors are convergent, and convex mirrors are divergent. So it's opposite with lenses. Well, if I send rays of light into a concave lens, now I'm going fast to slow, so I bend towards the normal. Now slow to fast, so I bend away from the normal. And in this concave lens, my parallel rays of light would emerge on the other side, not coming together, but in fact there would be a negative focal length over here somewhere back here. This is called a divergent optical device. Just like a convex mirror, a concave lens causes light rays to diverge. All right, now there are lots of practical uses for this. When I think of convex lenses, this is probably more common, and you probably have experience with magnifying glasses. A magnifying glass can be held in front of something to make the image appear larger. But we also, of course, use these in glasses and contacts. If you need glasses to correct for poor vision, you might either use a convex lens or a concave lens. Convex lenses are used to correct for hyperopia, that's farsighted. That means you can see things far away but have trouble seeing things in focus close up. The convex lens in your glasses or in your contacts would help to bring light together earlier so that it is in focus on your retina. But if you have myopia or nearsightedness, then you have trouble seeing things far away, but an easier time seeing things close up. So a concave lens will correct for nearsightedness. Convex lenses are used for magnifying glasses, and also in a combination of two convex lenses can be used to make a telescope or a microscope, depending on which lens is placed in front. Concave lenses do not magnify generally. but they are also used in, for instance, camera lenses. Most camera lenses are convex. Even the little camera in your phone, here's my phone here, right here where the camera is capturing light, there would be a small convex lens there because divergent light from some source needs to come together to land on the sensor for that camera. But big fancy cameras with the SLRs and all that, they may have a collection of different lenses inside a single lens cylinder. Primarily they're using convex lenses to bring light together, but convex lenses often have something called chromatic aberration, which means that different colors bend to different degrees, and instead of getting a very solid focal point and therefore a very clear image, the edges of the image appear blurred. There's different colored blurring. So to fix chromatic aberration, you can use concave lenses in conjunction with convex lenses to repair that. So these are used in cameras as well. So lenses there. Now I want to show you, just like concave and convex mirrors form images, lenses do as well. Now primarily we're going to look at convex lenses because they make real images. And I'll start with just an object here. Let's pretend we have some candle. And this candle is placed in front of a convex lens. Well, the same kinds of markers we had for mirrors can be used here, but we're going to use a focal point on both sides, and a CC, center of curvature, might be present on both sides. Now, instead of bending it on the way in and bending it on the way out and having to use Snell's law to figure out where this is going to move, I will use something called the thin lens approximation, which says if my lens is thin enough, I can assume that all the bending happens kind of in the same spot. So I'm going to have my bending happening in the center of this lens, and I have my principal axis running through. My vertex is the point where they meet. My first ray in my ray diagram will come in parallel. So light coming from some light source, this candle, is going to come in parallel, but parallel rays of light always pass through a focal point. So there is one ray of light. Well, the image could be forming anywhere here, so I need to find where divergent light rays converge to form an image. So the second ray goes symmetrically. Instead of going in parallel and coming out through the focal point, it's going to come in through this other focal point, and after hitting the lens, it will come out parallel. Already I see an indication that my image will form here, but just for fun, the third ray...
All avid students going on the high ropes course, need to be in the commons area. We're leaving in a few minutes.
Okay, important announcement. The third ray goes through the center, the vertex, and keeps on going. Does not steer or bend at all. I didn't draw this perfectly, but that's okay. And I know that the image is going to form somewhere here. Wherever the light came from, it spreads out from that point and then comes back together, coming into sharp focus right here. And I see that I have an image. Now, because the object was far from the lens and was beyond the CC, the image will be somewhere in between the focal point and the center of curvature. If I put this candle very, very far away, almost at infinity, this image would form on the focal point. But if I bring the object closer, the image forms farther away. If the object is on the center of curvature, the image is on the center of curvature. Same size. If the object gets even closer, the image forms farther away. If the object is on the focal point, we get no image. An object placed at the focal point, light rays would strike the lens and simply come out parallel. Those parallel rays would never converge to form a crisp image or a focused image. And if this object is placed even shorter, even closer to the lens than the focal point, there will be images, but they will not be on this side in the real world. They will be in the virtual world. Similar to concave and convex lenses, real images form where real light can land on a real piece of paper to form a real image. Light passes through lenses to form images here, so any image on this side will be real. Real images over here. Light does not typically hit lenses and bounce back and form something here. But you can get virtual images forming here, just like with mirrors. So images forming on this side will be virtual images. In our computations, when we get a DI that is negative, that's going to be a virtual image. If I have a positive DI, or positive image distance, that is a real image. And we'll see in the next video, just as this is very similar to the mirror ray diagrams, we actually use the same equations to determine where our image forms, find the DI from the DO and the focal length, and to relate the height of the image and object to the distance of the image and the object. So we'll do some with these in the next video.